My name is Dr. Thomas Hayes. I'm the Assistant Professor of Practice in Aerospace Engineering at the University of Oklahoma. I'm pleased to share with you the work of past and present aerospace capstone teams that goes a bit beyond the average expectations of our class. While all of my capstone students receive a short first exposure to the computational methods highlighted here, those who wish to adopt a competition team technical role or who become personally interested in developing a skill often take their involvement with engineering tools to a higher level than required. This has resulted in some continuing into CFD-based master's programs, being hired into highly competitive aerospace design and optimization jobs, and most importantly, leaving their undergraduate aerospace engineering studies with a very useful set of capabilities. This overview will cover the use of rendering tools, vortex lattice aerodynamic software, computational fluid dynamics, finite element analysis, multidisciplinary optimization, and electric propulsion modeling by aerospace engineering senior engineers. While students using these tools for the first time in an open-ended design purpose are certainly not experts, the skills and interests they develop after having some initial success with software-accelerated design and engineering lead to a larger volume of questions and conversations in class to help to unify their understanding of aerospace subdisciplines. One of my personal investments into Capstone has been the creation and maintenance of a MATLAB-based mission simulation and optimization code used by our Capstone class as a lesson and the DBF competition team as a tool for optimizing the aircraft and strategy. The code utilizes Reinhardt's leapfrog optimization method to accept constraints and provide optimal outputs from the competition mission simulations. Students are able to write their own structural weight model and aerodynamic drag models to interface with the base mission simulation to then produce performance plots and predicted competition scores. Multi-threaded processing through MATLAB's parallel processing toolbox has been added to the leapfrog code to shorten the amount of time required to generate optimized vehicles for many different sets of competition weather and opponent strengths. Multi-threading took our broadest studies from 8-hour runtimes down to below 30 minutes in 2020. The creation of an electric propulsion code began as a tool to benefit the DBF competition team, but is now used in a Capstone lesson module and in multiple UAS research applications. It is a useful tool for finding properly paired sets of permanent magnet DC brushless motors, speed controllers, and fixed pitch propellers for the airplane's power requirements. The tool can predict partial throttle operating efficiency in steady flight and give estimates of overall flight time as a function of velocity when provided a curve defining power to the flow requirements of the UAV. This tool has been successfully implemented on slow aircraft less than 1 pound to 100 mile-an-hour plus designs meant for operating near supercell storms. I'm pleased to introduce to you the 2020 Design Build Fly Aeronautics lead Nye Herndon and present Boomer Rocket Team Chief Engineer Tyler Swisher to further discuss their use of advanced computational tools in aerospace capstone.
In order to design an aircraft, such as for the AIAA Design Build Fly competition, aircraft models must be created to accurately represent the aircraft being designed. Other factors, such as the environment, propeller models, aerodynamic models, etc., must be generated as well. The advancement of computers and highly parallelized software packages allows for complex models to be developed for Design Build Fly. This was advantageous as it allowed students or teams to develop relatively accurate sizing, aerodynamic, and even electric motor models in order to design their aircraft. With powerful engineering and scientific computing packages, rapid iteration of designs becomes possible. In addition, it allows for a reasonable amount of time between design iterations. This ability to quickly and accurately simulate any particular design a team chose allows for complex trade studies in order to determine an optimal aircraft and refine a chosen design. These figures show how these models and simulations drove the University of Oklahoma's Design Build Fly aircraft in terms of banner sizing and passenger count. These models can become highly advanced and contain a large number of modifiable parameters. Once again, having efficient and powerful multi-threaded software allows for multi-variable optimization across as many variables as a team chooses. This could be as limited as just 2 or 3 variables, or as advanced as performing optimization across a 12 or 13 variable space. It also allowed for Pareto optimality frontier studies against uncontrollable variables such as wind speed during a competition flight. While this tool is powerful and can allow for rapid iteration and a global perspective, allowing a team to look at widely different scenarios and designs, yet still have some measure of confidence in choosing a near optimal design, it can also encourage students to generate unrefined models. As can be seen, this solution, while indicative of broad trends, shows poor convergence. This is caused likely due to model deficiencies. Finally, it can allow students to use computation as a sort of lever by which to force a solution without due consideration as to whether the garbage in, garbage out principle should and can be applied. Finally, when it comes to aerospace, modeling of fluid dynamics reigns supreme as a computational challenge. Simple methods such as vortex panel codes can be run almost instantly with modern computing power, allowing students to arrive at good solutions. Additionally, modern CAD CFD packages allow for the simulation of highly complex flow regimes with ease. As can be seen, even a propeller disk can be roughly simulated even in these software packages, which are relatively friendly to use. Once again, however, the question arises whether or not complex methods truly yield better results. As seen, while the vortex panel solution is more rudimentary, it still yields a highly usable result in a small percentage of the already impressive time it takes to run CFD. Regardless of the results and success, these methods benefit students in helping them to understand the complexities that are the reality of aerodynamics and aerospace engineering, but yet also apply solid engineering principles to achieve a good solution on time and under budget.
Hi, my name is Tyler Swisher, and I'm a senior aerospace engineering student at the University of Oklahoma. Computational fluid dynamics was simulated on the entire vehicle. We specifically wanted to compare coefficient of drag results from the simulation we were using in OpenRocket. We ran the CFD at Mach 0.96, our max velocity with respect to local speed of sound, and resulted in a coefficient of drag total of 0.939. compared to OpenRocket total coefficient of drag build of 0.88. OpenRocket outputs this table with respect to Mach input. The SOLIDWORKS CFD resulted in a slightly higher CD value, which helps give the team an idea of how accurate OpenRocket is at transonic Mach numbers compared to CFD and SOLIDWORKS. An equation solver for coefficient of drag was inputted for the CFD study to solve as a global goal to converge a result on. Vorticity circulation aft of the motor retainer on the booster subassembly helps visualize where some of the components of drag are really coming from. Using SOLIDWORKS integrated finite element analysis software, I simplified a nonlinear dynamic load into a straightforward static FEA simulation, where a derived static load was placed on the underside face of the U-bolt connection to the avionics bay. SOLIDWORKS FEA allowed the simulation to be ran on the entire assembly with known material properties, fixtures, contacts, and loadings inputted. This outputted a factor of safety of 3.3 with a 500 pound force loading and a conservative factor of safety of 1.65 with a 1,000 pound force loading. Using SOLIDWORKS add-on Photo360, images can be immediately brought to life from their standard viewport. Additional lighting and material appearances are customizable as needed. Here we can see the immediate difference using Photo360 and SOLIDWORKS has on our folding quadcopter. Parameters like shadows, reflection, ambient occlusion, bloom, transparencies, sample count, and lighting were adjusted to improve the realism of the overall final image. Using SOLIDWORKS explosive views, a keyframed animation was created to help better visualize the assembly of the booster subassembly. Advanced camera mates can be used to follow 3D sketch lines as desired. Transparencies and component movement speeds can also be keyframed, where the software automatically interpolates between two given keyframes. SOLIDWORKS integrates Photo360 as a built-in render add-on and can be used as an option when exporting the animation. The animation sequence can also be exported directly into SOLIDWORKS Visualize, which gives more options in setting material appearances and overall lighting for accurate scene visualization. SOLIDWORKS CFD was conducted on the quadcopter during a falling descent phase. Our team's quadcopter uses 1300 kV motors on 4S batteries, resulting in an RPM of 2024. Extruded bodies were added to each of the prop's rotational volumes. During this setup of the CFD study, those bodies were assigned as rotational bodies and set to the matching motor's RPM. Incoming flow was projected bottom to top of the drone at 30 feet per second. Resulting transparent isosurfaces are shown for the range of 34 feet per second to 500 feet per second. This study was mainly conducted more as a SOLIDWORKS learning project than a impacting design project.